Hello and welcome to Fresh Thinking by Snowden Optiro, a podcast where we delve into the technical aspects of the mining industry. My name's Tarrant Elkington, I'm General Manager. Today we're going to go back into the world of processing and learn a bit about optimal design of comminution circuits in mining projects. And joining me to talk about this is Dr. Lorenzen. Leon has more than 40 years of experience in processing, for operations, for research, and in consulting as well. So, Leon, thank you very much for joining us.
Oh, thanks. It's a pleasure.
So the topic today we're going to talk about is around comminution design. Can you just tell me firstly what is comminution?
Okay, comminution circuit is basically I call it a front end or the dry end sometimes, but it's not always dry because milling is wet, but it's a front end of the pond where you actually take the run of mine ore and you actually crush it first and then grind it to a particle size which you can actually put through the plant and there's two things to do it. One is to liberate the valuable metal, and the other one is actually to make the material more handleable to handle. You know, you can't use 800 millimeters or 1 meter blocks, and just move them around. You obviously have to put them on belts and things like that. So you're actually breaking it down. It is energy intensive. It's the most energy intensive part probably of your processing circuit, except if you have roasting and other things. But that is energy intensive, and it drives your throughput. It drives what you can put through the plant. If there's a bottleneck or things, then you have a problem with your comminution circuit. So it's a very important circuit for you to design effectively, and there's different flow sheets and options.
And so what are the typical options that we use in this space?
So the first of all is you need to understand the ore characteristics, and the ore characteristics is things like hardness, abrasiveness, toughness. That's the things that we'll test those to understand what is actually driving the breakage characteristics of this ore or ore body. And typical, you basically have typical processing plants. You have 3-stage crushing and a ball mill, for example. You'll have a single-stage crush and a SAG mill, which is a semi-autogenous mill, which you actually use the ore material to mill itself with some small amount of balls. Or you'll have a 2-stage crushing with a high-pressure grinding roll with a ball mill. Or you'll have, as we call it, an SABC circuit, which is a SAG and a ball with crushing and interstage crushing as well. So, and then you have ultrafine grinding, which is a VertiMill or an IsaMill or a HIGmill. That is grinding flotation concentrates and things like that. So there's a variety of circuits that's available, and they all have either crushers or mills, which is very expensive pieces of equipment capital, and they obviously have operating because they have liners and they have balls and etc. So they drive operating costs and capital costs to an extent. If it's a really soft ore body, it usually doesn't really that seriously. But as soon as an ore body is becoming classified as hard, it is a major issue how you develop that grinding circuit for the optimal value that you want to achieve. So those are roughly the circuits.
And when you say optimal, like comminution design, how do you measure that optimality?
So there's two ways to do it. There's two ways, and they should be basically in series. And sometimes people lose or say the first one is you will do this test work, you'll do the characteristics, and then you'll model the best circuit according to regrind. Sometimes you have to take some material back, so you do a mass balance and then around it. So it gets modeled. Okay. And that gives you, say, maybe sometimes they say 2 circuits can work, but the 2 circuits might be easier to operate, the one, but more in capital or, so there's other factors playing around. The second part of it, which should be in series, is which I call the optimal economic design. So the optimal economic design might not be the optimal capital. You might find that one circuit is capital intensive and it sounds like, oh, no, I don't want to go there. It's too expensive, etc. But the optimal economic design look at the capital costs and the operating costs to achieve the desired gold recovery. So it's very much fixed to the grind size that you need to achieve to liberate the metal. So good example to give you is if you have a material and you grind it to 106 microns and you get 93% gold recovery, it gives you a certain amount of ounces, right, through a certain circuit. If you take that same circuit and you grind it to 75 microns, it's more energy, it's maybe, etc., but it might give you 95% gold recovery and a certain amount of ounces. Now, to grind it from 106 to 75, the cost of the capital and operating costs versus the financial revenue you obtain by getting 2%, it have to be measured to each other. So what happened in the past is people always go for ounces, the maximum recovery. They want 99. They want, if the number is bigger, it's better. But the energy that you spend in getting that bigger number is so much that the MPV is actually not optimum. So we have some models where you can look at the optimum MPV for different circuits, depends on the grind size. It's very much linked to the grind size and gold recovery. So you'll have to have gold recoveries at different grind sizes, and you have to have that for different gold comminution circuit, for example. So different circuit will have. And then you will find, okay, that's the best circuit. It can work. Technically, it's 100%. Everything is right. But that is the best economically for me to go for. It's not, okay, I like that circuit, I don't like that circuit, I want 98%, I don't, but eventually it costs you a lot of money.
I guess it's about understanding where it sits in the broader scheme of maximising the project. And I guess maybe we find, operations as they go into production, they tweak things to push more in one way or the other to try and maximize that economic production, but it's better to get it right up front, right?
The other complexity that plays a role is back to the life of mine that we spoke about previously in one of the podcasts. The interesting part of that is you might have different domains. You might have oxides and different fresh domains, and they have different ore characteristics and hardnesses. And sometimes something which is designed for a very hard ore is not the best designed for a soft ore. And you have intrinsic problems then of throughput and etc. That's why you have to understand that actually you're building a comminution circuit for the life of mine.
Yeah.
And that is a very important thing about it. And it's not where you can cut capital. And it's also not where you also can say, okay, I need to cut some operating costs here. And that's usually where they looked at. But yeah, if you have a very hard ore body and your gold recoveries is not really exponentially increasing as you get into the 90s, you have to be very careful to select better gold recoveries for the design or a smaller grind size just because you think you're going to get more out of it. The power cost and the operating cost, the power cost is one, and then also the capital and operating cost is just going to take you out of that financial benefit that you actually gain.
Absolutely, and if we were just zoom out even further into that whole system, like people often talk about mine to mill, where you sort of bring your blasting into so your blasting is like the first breakage that you do of your rock. How does that play a part in your comminution?
It's very important because blasting techniques improve quite a lot. And again, if you asked me 20 years ago, what is the average ROM pad size that we look at, you will find that people will say something to about 1.5 meters on the ROM pad. Piece of rock can be accepted. It's very seldom that I see any gold plant or any processing plant nowadays being designed for anything bigger than 800 millimeters. So it's less than a meter, and that because it drives the crusher that you put in and how much you have to, so it's driving everything so if the more you can do underground, it's easier to bring it up or even open pit, that's important. And it's also easier to actually deal with it within the processing plant because it's easier to handle, first of all. And second of all, if it's hard, it's easier to further break down. Where a big piece, it takes stages. Everything is there. It's not an easy process to follow. But yeah, the blasting is that is an integral part of that.
And I guess that one final question just around, have projects designed a comminution circuit and it's just failed.
Yes,
You know.
there's good examples.
Yeah.
And it's not failure that it's always a failure for the whole life of mine, but it's usually failures where it was designed specifically for a specific domain and lithology. And that might be only 3 years of the life of mine, but it is difficult, and they want the throughput then. But, the rest of the material. So a good example is if you have very hard ore and you have very soft ore. And the soft ore, like oxides, can be maybe 2 years of life of mine. Now, if you're it's a different comminution circuit. And it sounds easy. No, if I have soft ore, I just push more through. But sometimes that soft ore have clayish or viscous material or handling issues or other issues. And it's not the same mill that you put in, same liners that you put in. You need to have the life of mine picture. Yeah. Otherwise, you're not. So the guys who model there, they like to have everything on life of mine and information because they will tell you where your bottlenecks will be.
Yeah, like I know of examples where people have chosen maybe a cheaper crushing option, but it works for the average, but it's the outliers that you've got to deal with at that point,
And I always say, if you have a type of mining system where you actually can mine much quicker than processing, you can blend, you can do a lot of things. But if you don't have that, so a big warning sign is an underground mine. It's you're treating what you're getting. It's not that you have a lot of stuff on the wrong pad. Yeah.
Well, it sounds as if it's something that is really important to get right from the outset, because it can be quite expensive to change it once you get into operations, right? Yeah.
But it's also a good thing because you can there's ways of dealing with it, so you can actually move capital to year 3 if it's needed. If you need an extra mill, for example, for that stuff, which only come into year 3, you can change things. You can actually look at, but you need to have that information available. Yeah. So there's ways to deal with the capital side of it as well.
Yeah. So, no, thank you for sharing your insights and today on this topic. And if you liked what you heard, please subscribe to our podcast so that you can hear future ones. Subscribe on Spotify or our YouTube channel. I look forward to speaking to you on future topics on fresh thinking.